We have one final topic to cover in this series on chapter 5, that is external flow. So far, we've focused on heat transfer problems, and we focused on issues of diffusion of momentum, that is coefficient of frictions. The final element has not been covered in the lecture notes. Instead, I've opted to add a few slides in your overheads, and that's 5 slides at the end. So I'm asking you now to go to slide number 37. Which is the start of our discussion on mass transfer. I'm going to start by just providing a few definitions with the help of a sketch like the one that's shown here. So what we're interested in is flow over a flat surface. The flow is of a mixture of species A and B, so binary species mixture. The conditions are fairly simple. We assume that the flow is uniform when you're away from the zone of influence of the plate. We also assume that the concentration of the species A, written Ca infinite to mean away from the plate, in the free stream is uniform, whereas the condition on the plate are different from the condition in the free stream. That is CAS, which is the concentration of species A on the surface, so S stands for the surface, is going to be, in this case, higher than in the free stream. And that's why you see the profile going to the left, that is decreasing as you move away from the plate surface. The region of influence on that concentration is called the concentration boundary layer. Its thickness is written delta C, C for concentration. So this is very similar to what we would have discussed in the context of heat transfer. The profile for temperature would look exactly like this one in cases where the temperature of the surface is greater than the temperature in the free stream. The transfer of mass from the surface to the free stream can be driven first by evaporation at the surface or sublimation, depending on what kind of surface you have here. So you can have a phase change from liquid to gas or from solid to gas. But that phase change creates a higher concentration of the species A at the surface, which then is diffused or convected away into the fluid stream away from it. Diffusion can be given by Fick's law of diffusion, and that applies to only the very, very narrow region near the surface where the fluid is assumed to have the same velocity as the plate itself. And in that case, we have a diffusive process. That is, we have a process that's driven by gradients of concentration evaluated at the surface and in the direction perpendicular to the surface. The relationship or proportionality between fluxes and these gradients are called the diffusion coefficient, DAB. The convection takes place away from that thin layer into the fluid stream and is written, as was the case for energy convection transfer, HM, a convection coefficient multiplied by the difference in concentration from the surface to the free stream. Both of them relate to molar diffusion or molar flux, that is an amount of moles transported per unit surface area and per unit second. All these definitions are given on the next slide. You see here the flux expressed in molar form, that is molar flux and rate of molar transport. And that means that we define the transfer of mass in terms of the number of moles, written in kilomoles in the SI units, per unit time and surface area, meter square, for the flux, and for the rate of heat transfer of mass transfer, kilomole per second. If you want to define the amount of mass that is being fluxed, then you write it as m dash dash, and the units are kilogram per meter square for flux and per second, whereas for rate of mass flow is kilogram per second. We switch from one formulation to the other by taking into account the definition of the two types of concentration. You've got the molar concentration and the mass concentration. You see that if you multiply the molar concentration by the molar mass, that is the amount of mass per kilomole, if you multiply these two, look at the units, kilomole and kilomole cancels out, and you end up with kilogram per meter cube. That is the units of the mass concentration. We use the rho letter, the Greek letter rho, to mean mass concentration because the units are the same as the units of density. The convection coefficient is a convection mass transfer coefficient, HM, has units of meters per second. That is the same units as velocity, so sometimes it's called a convection velocity. The binary diffusion coefficient, DAB, is something that we need in order to characterize the diffusive flux. We have a few values given here in the next table. So just to take an example, imagine you've got a substance B, which is your carrier phase, is liquid water. Within that liquid water, you can have dissolved carbon dioxide, for example, which will be driven into the liquid phase by the dissolution of carbon dioxide in the gas phase present perhaps over the interface of the liquid. And if you do have a high concentration of carbon dioxide at the surface of the water, then you will get a diffusive and convective transport of that carbon dioxide inside the liquid phase. And that's the coefficient DAB for that special mixture of carbon dioxide dissolved into the liquid and the liquid water. Once you have these definitions, it's useful to calculate the total rate of mass or molar transfer. And that's what's given down at the bottom. But before, we've got the formula for the fluxes. We've already discussed this one. If you want to go from the molar flux to the mass flux, all you do is you substitute the definition of the mass concentration for the molar concentration, which is given here. That is, Ca is equal to rho A divided by Ma. So if you put that rho A divided by Ma here and rho A divided by Ma, and you bring the Ma to the other side, you get this equivalent notation, which we already discussed. If this quantity is uniform over a surface, you just need to multiply the flux by the total area to get the rate of mass flow. But if it's variable over the surface, then you need to integrate that flux over the area using this formula. But because, or not exactly this formula, just using the part of the formula that's here inside the integral. So if you put all this inside the integral instead of that quantity, then you will end up with the total mass flow rate m dot as. By some manipulation, you can show using the definition of the area weighted average of the coefficient that this is equivalent to the area weighted average convection coefficient multiplied by the area and the density or concentration difference. Okay, so the only difference when you take into account variability is that instead of a local value of HM, you use an area weighted average. Now let's look at a few other definitions. How can you calculate those molar concentration, for example? So we're looking at an example where instead of a mixture of A and B, we've got just a species B in the gas flow over a liquid film. If we have that, nature will be such that it will try to take on or evaporate species A, which is not present in the species B gas flow here. So there will be a lack of equilibrium. It will be essentially devoid of any species A there. So you will have an attempt at equilibrium. That is, the natural process will be such that you will try to get the saturation concentration of the species A there. Saturation concentration is the maximum possible concentration of species A in that gas above it. And nature will try to achieve that. Will try to take away the molecules from the liquid to bring it into the gas phase above it so that it reaches that saturation concentration. So we can assume that the concentration at the surface or at the interface between the liquid and the gas will reach that saturation concentration. And from ideal gas law, then we can calculate that saturation concentration in terms of the partial pressure of species A. That is, if you take the partial pressure of species A at saturation and divide it by the constant R, the gas constant R, and the temperature S, then you will end up with that concentration there. You can do the same. We know the relationship between these two, so we know how to get the mass concentration equivalent. The mass concentration at saturation is generally tabulated. If you take, for example, water, a table on the properties of water, you will see at a given temperature that you have the saturation condition, or you have the gas value of the specific volume of that water in gas phase. So if water is in gas phase at a given temperature and pressure, it will have a certain specific volume. So the mass concentration is the inverse of that specific volume. The units of specific volume of the gas phase would be the volume of a kilogram. So you take the inverse, it gives you the kilogram of the volume, that is the density. So we'll have a look at that in the context of tutorials. But you can calculate those concentration from tabulated data. In the free stream itself, you also have an equivalent definition for the species concentration in terms of the same values, but at condition in the free stream. Now we have a final definition, which is the relative humidity, written phi infinite, and it can be defined in terms of the pressure, the concentration, two forms of concentration. Minimum is 0. If you've got 0 species A in the free stream, then you have no relative humidity. So humidity relates to water. So we're really looking at here, liquid is water and the gas is air. And so if you have liquid in here and you have 0 amount of water in gas phase, then we have 0 relative humidity. But if you achieve the saturation concentration in the free stream, then you've got 100% saturation value, or the relative humidity is 1. That is the pressure, the partial pressure of species A in the free stream is going to be equal to the partial pressure at saturation. When the two are equal, you end up with a ratio of 1, that is 100% relative humidity. Same thing would apply if you have the maximum possible concentration, molar concentration of species A is the saturation concentration. So if this one is equal to the saturation concentration, you'll get a ratio of 1, that is a relative humidity of 100%. So all this is important. If you want to solve a problem where you have this kind of mass transfer from due to evaporation, then we'll have to have some handle on these values at some point. So to take a practical example, how would you get there? We know that liquids absorb thermal energy, and as they do so, they will evaporate. To evaporate at the liquid interface requires energy. So you will need to look at an energy balance in order to understand the processes that are taking place, including mass transfer. And an easy way to do that is to sketch our control volume, which includes the liquid and at the interface itself. We know we can get energy from the gas flow above it. We can also get energy from an addition to, or addition of energy from the outside. It could be by radiation, it could be by other means. You could have a heating element, or you can even have energy that comes from the liquid itself. But in that case, the process must be accompanied by a reduction in temperature of the liquid phase as the flow goes through the control volume. Okay. So essentially, any energy addition ends up being lost in terms of the energy required to drive the evaporative process. That's, if you look at it in the flux element, the flux of energy due to the evaporation can be calculated from the mass flux multiplied by the latent heat of evaporation. So that again is tabulated. So if you've got liquid water, in order to evaporate liquid water, you need a certain amount of specific energy, that is energy per unit kilogram of fluid, and that's what the latent heat of evaporation is. So if you multiply these two terms, it gives you the energy flux required for the evaporation. This type of equation is essentially the starting point for evaluating the amount of mass transfer, and you can easily extract it from that point. We'll see how to do that in the context of exercises, and we'll see how we can use information like this in order to understand how much is going to be, or what is going to be the relative humidity of your mixture if it's a process that takes liquids into the gas phase. And we'll do that during the tutorials.